Hello everyone. In this session, we'll discuss a question on Green's theorem. So the question says, using Green's theorem, evaluate x square y dx plus y square dy, where C is the closed path formed by y is equal to x and y equal to x cube from 0 comma 0 to 1 comma 1. So it says that use Green's theorem and try to evaluate this. This is a line integral. This is a line integral, right? So we have to find this line integral. Of course, if they are saying using Green's theorem, that means it will be easier to find this line integral using the double integral. So before that, we'll have to see what is the region enclosed by this closed path, right? So it says the curve is, or the closed path is formed by the line y equal to x and y equal to x cube. Roughly I'm saying, let's cooperate on this, and let's say this is y equal to x and this is y equal to x cube, right? Then definitely this point is going to be 1 comma 1, this is 0 comma 0. Of course this line can be extended on the back side on the third quadrant, but since the region defined is from 0 0 to 1 1, so it will be in the first quadrant only. And to make this a positively oriented, we can say that this curve is going anti-clockwise. So this is the curve C. This is going anti-clockwise, you can see this. And of course this is the region enclosed. This is the region enclosed, right? So in that case, of course this is the region enclosed and we have to find this line integral, right? Clearly we can say that for this line integral, P is equal to x square y and Q is equal to y square, right? These are the terms, and this line integral can be changed into a double integral with dq by dx minus dp by dy for the region, let's say R, right? Now what is dq by dx? This is q. With respect to x, the partial derivative is going to be 0 minus dp by dy. So this function is x square y, and differentiation with respect to y will give you x square, so minus x square, and this is dA for this region R. I'm still not getting into dA now, but now we will have to do this. Let's see what will be easier. Of course we have seen what is double integration and how to take the variables and how to take the limits, how to define the rectangular elements, right? We are clear with all the elements. So in that case, somewhere it will be convenient, sorry, this is x, somewhere it will be convenient to take the vertical elements or vertical rectangular elements. The reason being, the elements for y will be easier compared to x. So let's say this is the element we are talking about. We can clearly see the starting point or the lower limit of this rectangular element lies on this line y equal to x cube. right? This is the line or this is the curve. So the lower limit is, let's write it here, cube, and the upper limit is on this line. This line is y is equal to x, so it is x. The term is minus x square dy dx, because we are taking the vertical rectangle here, so we'll keep it dy dx instead of dx dy. And the limits for x will be the region for which this vertical element is defined, and it is defined from x equal to 0 up to x is equal to 1. So that makes the limit equal to 0 to 1. So now we have to find this double integral, and we can easily solve this and we can find the answer, right? So let's do it. The first integration will be with respect to y, so x square will remain as it is and it will become minus x square y. The limits are x cube and x, and then we have to integrate this with respect to x with the limit 0 to 1, right? This will give you minus x cube. So what we can do is, using this sign, using this negative sign, we can change the limits. The upper and lower limit can be exchanged, and this becomes x square and x cube. So x to the power of 5 minus x cube, and then we can integrate this with respect to x from 0 to 1. So this becomes x to the power 6 by 6 and x to the power 4 by 4. The limits are 0 to 1. So for 0 it will be 0. This is going to be 1 by 6 minus 1 by 4, which will be mm, minus 1 by 12. So this will be the answer for this case.